Good morning. Today we're going to be looking at section 1.1, modeling and equation solving. And we start out with 4 steps that we use to help solve our problems and problem solving. And the first step is we want to understand the problem, figure out what it is, clarify, identify the information needed to solve it. Really read the question to see what is being asked and making sure that you understand clearly what it is that you're trying to solve. Then second, you're going to develop a model. All the tools that you've been given from preschool all the way up to now to high school are going to be utilized then as we go and we develop this mathematical model. So some of those things you were thinking, when am I ever going to use this? As we get into some of our higher level thinking, we will see, we'll be able to pull some of those tools out and utilize that to help us develop the model in which to solve the problem that you defined in step number 1. And sometimes in developing a model, drawing a picture, labeling a picture, equations, any of those are rational ways in which to solve. And then number 3, you actually go ahead and you solve it using the model that you found in number 2. And we're going to be solving in this class numerically, algebraically, and graphically. And we will be talking about that here in a second. And then, of course, you always want to interpret after you get an answer, after you solve. You want to ask yourself, double check, did the answer actually make sense? And plugging it back in, obviously, if you're trying to find an answer for distance, if you end up with a negative number, probably not a great solution. So going back and making sure, first of all, that you understood, is the model that you developed for the problem accurate? And did you make any mathematical errors as you were solving? Are good questions to ask as you go through to see after you are working the problem and interpreting the problem. So in pre-calculus, we're going to be looking at different types of mathematical models. We're going to be looking at numeric models. And when I say numeric, I'm meaning that you're going to be looking at a table. And if you grab your graphing calculator, you can go to second graph, and then that gets you a table. And so a lot of times we're going to be pulling information off of this table, and that would be actually graphically as well, or excuse me, using our technology as well, but using the table here on the calculator. Sometimes the tables are given for us in written form, but when I say numeric, that's what I'm referring to, is looking at a table. Algebraic would be just if we're solving just a regular equation. Equation of a line, y equals mx plus b, would be an example of something that would be algebraic. And then a graphical model would be, again, utilizing our calculator and going to a graph and looking at a graph and pulling information off the graph. There is a fourth method, and that is technologically. Actually, I'll keep it in mode, technological model. And that would be utilizing our calculator. So sometimes number 4 is used in conjunction with these other. It also could mean using a computer in order to solve our problems, what we're looking at. Okay? So steps to problem solving, probably not new information to you, and the types of mathematical models that we're going to be looking at here in pre-calculus. All right, so just zeroing in on some quadratic equations, okay, utilizing what we have just talked about here. We can solve a quadratic equation in several different ways, just depending upon what kind of a quadratic we have. We can solve it using the factoring and zero product property. That's nothing more than putting something as factors and then setting each one of those factors equal to 0 in order to solve to find our solution. And so that's utilizing the zero product property. And again, we will look at that down below. Taking a square root, and so if we have y equals x squared, and we can take the square root of the x squared. Actually, that's not a really good example, but we'll see an example down here where we will be taking the square root, set it equal. So if I would make that y into a 4, that would be a better way in which we would take square roots of both sides. graphing and finding x-intercepts, so we'd plug the equation into our calculator, and we would use the calculate button in order to find our x-intercepts, and we will again see an example of that. And then our fourth method that we're going to be using in this class is using the quadratic formula, which we have stated down here. We have the quadratic equation here in standard form. We have a x squared plus bx plus c, pulling out the a, b's, and c's to put into our quadratic formula. X equals opposite of b plus or minus square root b squared minus 4ac all over 2a. And so you will have to show mastery of this, and then as we move forward, we might find a special program that our calculator will be able to do to help simplify the quadratic formula for us. So first of all, let's solve this equation that we have here by factoring. So the first thing we're going to do is we're going to set up an x. And because our coefficient here is not 1, it is something greater than 1, we're going to use what I call the AC method, where I take a, pulling the a off of the standard form of a quadratic equation, and multiply it by c. 2 times 3 is 6. I'm going to put 6 right here. And then the middle term is going to come down here. This is just a graphic organizer to help us keep our thoughts and what we're doing kind of in better order. So what I'm thinking in my head is I need two numbers that multiply to get me 6, but also add to get me 7. So we know that that would be a 6 and a 1, because 6 times 1 is 6, and 6 plus 1 is also 7. That 7 is positive, the 6 is positive, so I do not need to worry about any negative numbers in this solution here. Once I have these two numbers, what this is going to do, it's going to break my middle term into two separate terms. It's going to break into 6x and 1x. So I'm going to rewrite this equation as 2x squared. The first term stays exactly as it is, but the 7x is going to get split into two different terms. So 2x squared plus 6x from the 6 here, plus 1x, the 1 there, and then the last term will stay as it is as well. So I have 2x squared plus 6x plus 1x plus 3 is set equal to 0. Again, the first term stays and the last term stays. The only thing that's getting broken up is the 7x from these two terms right here. Then I'm going to go into a method called grouping, where I imagine two parentheses around the first two terms and parentheses around the last two terms. And what I'm going to be pulling out is a common factor in both sets. So first of all, a common factor of 2x squared plus 6x would be 2x. And then I immediately write down a parenthesis because that is my common factor that's going to be multiplied by the remainder of what's inside this parenthesis. So I look at this as a division problem. 2x squared divided by 2x leaves me with just 1x. 6x divided by 2x is a positive 3. Then I move to the second set of parentheses, and 1x plus 3 does not have a common factor other than 1. So I pull the 1 out, and I'm left with x plus 3. The two sets of parentheses better be the same, because my next step is again pulling out a common factor. A common factor of this term and a common factor of that term leaves me with x plus 3. And then what's left is my coefficients, 2x plus 1 equal to 0. Then using the zero product property that we talked about above, I take each one of these factors and I set them equal to 0 and solve. So I get x equals negative 3 and x equals negative 1/2. That's solving by factoring using the AC, what I call the AC method, and then going into grouping with that. It says here to verify by graphing. So we're going to pull out our calculator. We're going to clear out, and I'm going to go to the y equals button. I'm going to clear out the equation that I had, and I'm going to type in the equation that was given. So I type in 2x squared plus 7x plus 3. And then I go to the graph button, which is to the far right, and I see that I have a nice parabola right there, and I would assume it to be a parabola as I have a quadratic, highest degree of 2. It is a positive coefficient, therefore my parabola is upward facing, and so all of that lines up. So what I'm going to do is I'm going to verify my answers. I found -3 and -1/2, and just by eyeballing it, it does look like it would be a -3 and a -1/2, but we know not to assume. So let's go to second trace, which is my calculate button, and I'm going to go down to number 2, 0, because I'm going to find the zeros on this graph. The zeros are where the graph crosses the x-axis. The zeros are the x-intercepts. So I follow along with the questions on to the left-hand side of my calculator. It says left bound, so I'm just going to use the left toggle button, and it means to the left of that first 0. So if you can just picture this is all to the left and over here is all to the right, that cursor is to the left of that 0. So I'm going to hit enter. And then it says right bound. So I take my cursor and I move it down below, which is then therefore to the right. Not much to the right, but it is to the right of that 0. I hit enter again. Guess, we can enter right through that, and then it will tell you right there what the 0 is. X equals -3, y is 0. -3 is what I have, so that checks. Now I move and do the exact same thing for the second 0. I repeat that whole process. Second trace gets me to calculate down to 0, and I follow along the instructions onto the left-hand side of the screen where it says left bound. So I'm going to move my cursor a little bit closer to the 0. It really doesn't have to be exactly right there, but it just needs to be to the left of this second 0, and I hit enter. And I then toggle up, and again I'm above, which is to the right of this 0 here. I hit enter, and I hit enter through the guess, and I see that I have another 0 at -0.5, which is the same thing as -1/2. That checks. That's how we can verify by graphing. Our next example is solving by square roots. And we can see that typically if with a quadratic, we'd set it equal to 0 and solve it either by factoring, quadratic formula, but by moving this over and setting it equal to 0, I probably have complicated the problem more than I have helped it. So to start out, I'm going to, noticing that I have a square, that if I take the square root of the left, I can also take the square root of the right-hand side. And knowing that a square root undoes a square, I am left with 2x minus 1 equals the square root of 9. We know that to be 3, but we know that to be a positive. It also could be a negative, so making sure that we include the plus or minus with that solution. And because I have 2, I'm going to have 2 different problems I'm going to work. 2x minus 1 equals 3, 2x minus 1 equals a -3, both of them, because my degree is 2, it's a quadratic, meaning I could have a possibility of 2 zeros. And so this allows me to see that I might have a solution here and I might have a solution here, assuming that they are real solutions. I add 1 to both sides, I get 2x equals 4. Divide both sides by 2, I have x equals 2. Adding 1 to both sides, I get 2x equals -2. Dividing by 2, x equals -1. And there's my first solution, and there is my second solution. You again could verify this graphically, and you would find that you would have a 0 at 2 and a 0 at -1. Okay, flipping your papers over, we are now going to solve using the quadratic formula. First off, I notice that I do not have this in standard form. So the first thing I want to do is make sure that my equation is in standard form, and I do that by moving everything over, keeping my x squared, my leading coefficient is positive, so I subtract my 8 over and add my 4x over, and putting it in standard form, I get x squared plus 4x minus 8. I then recognize that my a is 1, b is 4, and c is -8. Quadratic formula states that x equals the opposite of b plus or minus the square root, b squared minus 4ac, and that's a negative, all over 2 times a. Simplifying this, we'll try to do as much as we can without a calculator. -4 plus or minus square root. 4 squared is 16. -4 times 1 times -8 is a positive 32 all over 2. -4 plus or minus 16 plus 32 is square root of 48 all over 2. We can now take that, leaving it into radical form. I know that I have a perfect square in 48, so 48 is the same thing as saying the square root of 16 times the square root of 3 all over 2. What is the square root of 16? The square root of 16 is 4 root 3 all over 2. And because the 2 can divide into the first term and the second term, both, I'm able to simplify. So it simplifies down to -2 plus or minus 2 root 3 as your final answer. Typically, we want to leave our quadratic as exact answers with a radical, but if you would like to take that as -2 plus 2 root 3 and get a decimal, -2 minus 2 root 3, get a second decimal, you are welcome to do so. Okay, so then we're going to be using a graphing calculator to approximate this solution. But now we're looking at these two. We don't have quadratics anymore. We're into cubics, and we are looking, well, the first one. And this is just using a graphing calculator, so this is just getting some practice on using our calculator. So I go back to my calculator, and I'm going to go back to the y equals button, and I'm just going to hit clear, and it's going to clear out the equation that we had in there earlier. I'm going to type in x cubed. Here's my x button that I'm going to be using. To get the cube, I use the caret and then the 3 minus x minus 1. And what I did not do, I just showed you what not to do. After you have the cube, you want to use the right arrow toggle to make sure that you're out of the exponent spot. And so I had to, that was my mistake, minus x minus 1. That looks a little bit better. All right, then we go to the graph. And in your mind at this point, you should probably have an idea of what a cubic looks like. And there we go. And so we know, because our degree, our highest exponent, is a 3, that is the maximum number of zeros that we could possibly have as solutions for this graph. And so I look at this and I see 1 for sure, but this looks a little suspicious over here. I'm not sure if that's touching. My eyes are going bad. So we're going to calculate our zeros again. So I'm going to go to second trace, which is my calculate button. I'm going to go down to 0. And this says to the left bound, so I know I have a 0 right here. So I'm going to leave the cursor right where it's at because it is to the left of that. And now I'm going to go to the right, which is above, and hit enter. And it does look like I have a 0 at x equals 1.32, rounding to the hundredths right there. And it says to approximate. And so I do not need to worry about having an exact answer. I'm looking for an approximate for that. Now, if I want to, I'm going to zero in, move my cursor over to where I thought the 0 was, and I'm going to zero in. So I'm going to zoom in on that just to make sure that I know that it is not touching the x-axis. That graph is not even close to that x-axis, so I'm going to leave that alone. Therefore, I only have 1 0 for that problem. Our second one, go back to the y equals, clear out what you have, and we have an absolute value situation going on here. And we do not have anything set equal to 0 as we do here, so what we'll do is we'll move this over to the right-hand side and get it equal to 0. Sorry about that. That is a 3. Let me make that a little neater. And set that equal to 0. I subtracted 4 because that's a positive 4, and we can pretend as if the absolute value bars are parentheses. They act like that everything's inside is 1 solution, and so by changing the sign outside means I do not have to change the sign inside. So I'm just adding the absolute value of x minus 3 over to the other side. So therefore then, that is what I will type into my calculator and find the zeros for that. To find the absolute value bars, I'm going to go to second catalog, or second zero, and I'm going to get to the catalog, and I'm going to have to keep scooting back and forth. Sorry about that. And here's my absolute, ABS. It's the first one, so you just hit enter, and that will automatically put the absolute value bars there for you. So I do 2x minus 5, toggle over 1 to get outside of the bar, minus 4, plus, I need to get back to the absolute value, so second 0, which gets me to the catalog. Hit enter because that's the absolute value, and then I x minus 3, toggle out. I will graph that, so I hit that last graph button, and I notice I do not have the same axes that I had previous. Something doesn't look right. So if you encounter that with your calculator, just go to zoom and down to number 6. You want to get back to the standard set of x and y axes. And then you hit it, and then there I can see I have my absolute value graph. Knowing that an absolute value makes a nice V, I'm going to second calculate, I'm going to 0, left bound, and I'm going to be targeting this 0 here first, hit enter, right, I'm going to go below, but I'm not going to go to the second graph yet, or second line, and then I know that I have a 0 at x equals 1.3 repeating, or 1 1/3. Then I'm going to do the same thing, second trace to get to calculate, to the 0, left of the second 0, which is down below, hit enter, right, hit enter, and I see I have another 0 at x equals 4. Those are my two zeros for my absolute value graph. So moving on, we see that we have this fundamental connection that is connecting all kinds of synonyms for a solution. So if A is a real number that solves the equation, so it is the solution, then these three statements are equivalent. They are synonymous with one another. The number A is a root or solution. The number A is a 0. And the number A is an x-intercept. All of the graph y equals f of x, or y equals f of x equals 0. So you could see, please find the solution, please find the root, please find the 0, please find the x-intercept. They all mean the same thing. So don't be confused if you start hearing one or the other. They mean the exact same thing. Using a calculator can be very handy, but it also can prove to be kind of deceiving, because we can see misrepresentation of the graph, we can see hidden behavior in a graph. So you always want to make sure that you know what you're looking at by either zooming in or zooming out of a window. So for instance, let's take this graph, y equals 3 divided by, and notice the parentheses. If you have more than one term on the numerator or the denominator, you need to include parentheses. 2x minus 5, close the parenthesis. We're going to graph that, and we do have our standard axes, and I see we have a split graph. So let's look at, and it says, is there an x-intercept? Well, why in the world would we be thinking that there was an x-intercept? Well, let's go to the table, and if you notice that if I go to the point 2, negative 3, and then 3, 3. That may not seem very important to you right now, but looking strictly at the y values, I see that I go from a bunch of negatives, and now I'm going to some positive numbers. That is called, if I have a jump from a negative to a positive, or a positive to a negative, what I'm doing is I'm actually have to cross the x-axis to go from one point to the other. Let me just draw you. So if I have 2, negative 3, so 2, negative 3 here, and then I have 3, 3. Let's just pretend I've got, okay? if I would go from one to the other, connecting the dots, I would have to cross the x-axis according to this table. But strictly finding our solution, looking at a table and not looking at the graph, noticing, oh, well, gracious, that is an asymptote there. I've got a vertical asymptote there. If I was strictly only using the table to find my solution, I would have an incorrect answer. But by looking at the graph in conjunction with looking at the table, I can see that there would be a vertical asymptote. There's also a horizontal asymptote there as well. But so to answer this question, is there really an x-intercept? The answer is no. So you can then go ahead and solve to find that x-intercept. And we're not going to go ahead and do that, but the point was making sure that you utilize the table and the graph in conjunction with one another to make sure that you get the most accurate answer. All right, so let's look at this last problem. And we have a cubic, a very lengthy cubic. Going back to y equals, clearing out. I'm going to type that cubic in, making sure I toggle over to get out of the exponent. Minus 1.1x squared plus, that would be a minus 65.4x plus 229.5. I hit my graph and I see that I definitely have some interesting information going on here. I definitely have a 0 over here. If I would zoom out, we would see the entirety of this graph. And I see that I have a parabola here. And just by looking at the naked eye, it looks like I have 1 0 right there, okay? I know that I have, because I have a cubic, I know that I have a maximum of 3 zeros. So we want to make sure that we're not missing any. So what I'm going to do is I'm going to make sure that I am at the vertex of this parabola here, well, not really a parabola, but where the graph dips down, looks like it's touching the x-axis, and I'm going to just zoom in on that. And I'm going to see that the graph looks a little suspicious. I'm going to do another zoom. Oh my gracious, it is dipping down a little bit. Let's do one more. And there it is. I can now see that I do have that graph touching in 2 different places where originally on the full screen I would not have been able to determine that. So making sure that if something looks suspicious, make sure that you utilize the zoom button as you go in. And then I can still go to the second calculate in this window, and I still want to get to the left bound. So I'm going to go over here to the left of the 0, hit enter, to the right of the 0, hit enter through guess, and I see that I have a 0 at x equals 5. All right, I want to find this 0 over here, so second trace to get to my calculate. I want to get to the left of that 0, so it's going to be, in other words, below, hit enter, to the right, it's going to be above, so it's either below above or above below, depending upon where the 0 sits, situated on the graph. I hit enter through guess, and I have a 0 at x equals 5.1. And because those are so close in proximity, you could see why the graph would make it look very confusing, like there could just be 1. So the point of all that is to make sure that if you see something that looks a little suspicious, that you zoom in and don't just assume that there is only 1. That is called hidden behavior of a graph, and making sure that you see that.